Welcome to today's episode, where we're diving into the fascinating world of distributed systems with a particular focus on transactions. In our increasingly interconnected digital landscape, the reliability and consistency of data across multiple servers is absolutely vital. So what exactly are transactions? Well, at their core, transactions are sequences of operations that need to be completed in full or not executed at all. This principle, known as atomicity, ensures that databases remain in a consistent state even when failures occur. Imagine you're transferring money between two bank accounts. For that transaction to be valid, the amount has to be deducted from one account while being credited to another at the same time. If either operation fails, the entire transaction should be halted to prevent any discrepancies in your financial records. However, executing transactions across multiple servers brings its own set of challenges. The complexity arises from the need to coordinate actions that span different nodes, each potentially facing its own issues, like network failures or server outages. This is particularly critical in financial applications, where the stakes are incredibly high, and maintaining data integrity is essential. To address these challenges, we turn to atomic commitment algorithms. These algorithms are designed to ensure that all participants in a transaction reach a consensus on whether to commit or abort the transaction. One of the most widely recognized methods for achieving this consensus is the two-phase commit protocol, or 2pc for short. So, how does the two-phase commit protocol work? It operates in two distinct phases, the voting phase and the commit phase. In the first phase, a coordinator node kicks things off by initiating the transaction and requesting votes from participant nodes, which we call cohorts. Each cohort then evaluates whether it can commit to the transaction based on its local state. If every cohort gives an affirmative response, the coordinator moves on to the second phase and instructs all cohorts to commit the transaction. But if even one cohort votes against it, the coordinator aborts the transaction, ensuring no partial updates take place. This structured approach reinforces the importance of consensus in maintaining data integrity across the system. Now, while the two-phase commit protocol is effective, it does have its limitations. One significant drawback is its vulnerability to node failures. If just one cohort fails during the transaction process, it can halt the entire transaction, impacting system availability. This reliance on all participants being operational can be a critical weakness, especially in high-demand environments. To tackle these issues, some systems have adopted alternative strategies. For instance, Google's Spanner utilizes Paxos groups to enhance availability, ensuring that transactions can still be processed even if some nodes fail. By employing consensus algorithms like Paxos, these systems maintain a higher degree of reliability during transaction processing. An important aspect of the two-phase commit protocol is the commitment process itself. Once a cohort agrees to a transaction, it commits to that decision, meaning it's bound to follow through unless the coordinator says otherwise. If a cohort fails after agreeing to commit, it has to retrieve the final decision from the coordinator later to ensure it can operate correctly. This retrieval process relies on maintaining a decision log, which records the outcomes of transactions and replicates this information to any failed participants. This logging mechanism is crucial for restoring consistency in the event of failures, but it also adds complexity, as the system must ensure that logs are accurately maintained and accessible to all relevant nodes. Now, let's talk about the challenges that come with waiting for responses. The two-phase commit protocols need to wait for votes from cohorts can create additional hurdles. In cases where network links fail, the coordinator might experience delays in receiving those votes, leading to potential indefinite waits or message losses. If the coordinator doesn't get timely responses, it might choose to abort the transaction, which can disrupt operations and lead to inconsistencies. This brings us to the delicate balance that distributed systems must maintain between consistency and availability. The challenges of ensuring timely communication among nodes are a significant factor that system designers need to consider when implementing transaction protocols. Given the limitations of the two-phase commit protocol, enhancing availability becomes a critical focus for distributed systems. Techniques such as using Paxos groups or other consensus algorithms can help ensure that transactions continue to be processed, even in the face of node failures. These strategies aim to create a more resilient system that can withstand disruptions while still maintaining data integrity. As advancements in distributed databases and transaction management continue to evolve, they offer new solutions to the age-old challenges of consistency and availability. As technology progresses, understanding these mechanisms becomes increasingly important for developers and system architects. In summary, today's episode has provided an in-depth look at transactions in distributed systems, emphasizing their importance in maintaining data consistency and integrity. We explored the two-phase commit protocol as a foundational mechanism for managing transactions and discussed its strengths and limitations. As we navigate the complexities of distributed systems, the principles of atomicity and consensus remain essential for ensuring reliable operations. Understanding these concepts not only aids in designing robust systems, but also equips us to tackle the challenges that arise in our ever-evolving digital landscape. Thank you for joining us today, and we hope you gained valuable insights into the world of distributed transactions. Stay tuned for our next episode, where we'll continue to explore the intricacies of distributed systems and their impact on modern technology.